Okay, let's solve today's daily integral questions. I've already done the limit. It's actually a pretty simple one. Let's look at it together. So we're asked to evaluate the limit as n goes to infinity of sine pi square root of n squared plus 6/7 squared. Now, what you first need to notice is that this radical, as n goes to infinity, more and more closely approximates n. And so this whole sequence approximates sine of pi n, which is 0. So we have a candidate limit here, which we're not certain if it's actually the correct value for this limit, but it is a possible value for it. So what we first start by doing is by evaluating the limit as n goes to infinity of the difference of this radical and n. And it turns out, using some simple algebraic tricks, that this limit evaluates to 0. So then we can start to prove that this approaches 0. And the way we do that is using the epsilon delta definition, well, the epsilon n definition of a limit of a sequence. So we let an arbitrary epsilon greater than 0. And since we've shown that this sequence converges to 0, that means there exists an n0 such that this difference is bounded by epsilon over pi for all n greater than or equal to n0. So then we take the difference of the sequence and our candidate limit, and we want to bound that by epsilon. The way we do that is, well, we write 0 as sine of pi n, and then we use the fact that sine is Lipschitz, which means that we can linearly bound it from the arguments. So then we take out a common factor of pi, and then for n greater than or equal to n0, we've shown that this absolute difference is less than epsilon over pi. So this just means that this whole thing is bounded by epsilon, which completes our proof. Therefore, this limit actually evaluates to 0. And as you can see, I've already solved this, okay? And now let's start with integrals. So the beginner integral is, okay, it's actually very easy as far as I can tell. So now notice that there's already cancellation here. So this isn't actually what we need to evaluate. We actually just need to evaluate this. The x squareds can be removed. We can also change this to cosine squared. So we have cosine squared on the denominator, cosine to the third on the numerator. So this is actually just the integral of cosine x on the interval 0 and pi over 4, which is sine x from 0 to pi over 4, which is just square root of 2 over 2. And let's check the answer. And it's correct. Okay, let's move on to the easy. Okay, so I see that there is some sort of change of variable here because we have secant squared and tangent, but this cosine is not helping. So what we're going to do is we're going to use an identity that equates cosine of 2x to cosine squared of x minus sine squared of x. And we're going to write this as cosine squared of x minus sine squared of x all over cosine squared of x times 2x minus tangent x dx. I think we can factor out a cosine, but then we get 1 minus tangent squared, which we can't really do anything with. Effectively, Let's try writing the sine squared using the Pythagorean identity. We're going to get 2 cosine squared of x minus 1 over cosine squared of x times 2x minus tangent x dx. Oh, okay. So the next step is now to factor out the cosine squared. And now by letting u equal to the denominator, notice that the derivative of u is 2 minus 1 over cosine squared of x dx, which is exactly our numerator. So this is just du. So now we need to u of 3 pi to calculate the bounds of integration. So this would be 3 pi over 2 minus 1. No, plus 1. Yes, plus 1. And u of pi is 2 pi minus 0, so just 2 pi. So this is from 3 pi over 2 plus 1 to 2 pi of 1 over u du, which is just ln of 2 pi minus ln of 3 pi over 2 plus 1, which is ln of 2 pi over 3 pi over 2 plus 1, which I can simplify, well, kind of simplify to 4 pi over 3 pi plus 1. Okay, let's try this. This is a ln of 4 pi over 3 pi plus 1. No, plus 2, right? I think I did a mistake. Yes, this is multiplied by 2. Yep, and that is correct. Let's go to the medium and okay, I think I can already see how this is solved. So this is a classic family of integrals, the integrals containing values like x plus some radical of x squared plus or minus 1. So usually what you need to do here is let u equal this and then calculate the value of x using that. And it usually gives you a one-to-one mapping. But I think it makes more sense for the first step now to be an integration by parts, because the derivative of these radicals under ln usually is very simple. Let's see if I can. Okay, so 2x over 2 square root of x squared minus 1. Yes, so notice what happens now. If we make a common denominator in this parenthesis, you end up with x plus square root of x plus 1 minus 1 over x plus square root of x squared minus 1 times 1 over x squared minus 1 in the square root. So the derivative of that logarithm is just this, which is pretty good. So yeah, we're going to do integration by parts. We're going to differentiate the logarithm, and this will give us this, and we're going to integrate 1 over x squared, which will give us 1 over x, negative 1 over x. So the integral from 0 to infinity, ln of x plus square root of x squared minus 1 over x squared is equal to, well, negative ln x plus square root of x squared minus 1 all over x evaluated at 1 and infinity. which I think equals 0 because, yeah, this is of the form ln, well, something x over x, and x dominates in this case. So at infinity it equals 0, and at once it's ln of 1 plus 0, so ln 1. So this is just always 0. So then the integral is just equal to the integral from 1 to infinity of 1 over x square root of x squared minus 1 dx. Okay, so this is a trigonometric substitution that needs to happen here. Okay, so instead of trying an inverse hyperbolic function substitution, let's try simple trig substitution with secant. That should also work, because it is also true that secant squared of theta minus 1 is tangent squared of theta. So let's see how this works. So what we're going to do is we're going to let x equals secant theta. Then theta is, well, inverse secant of x. And dx is secant theta tangent theta d theta. Now, for x equals 1, the value of theta should be, well, 0, because cosine of 0 is 1. And for theta is on infinity, well, let's just do this. The value should be pi over 2. So this is actually just the integral from 0 to pi over 2 of 1 over secant theta tangent theta times, well, secant theta tangent theta d theta. So just pi over 2. Will pi over 2 work? Yes, so it is pi over 2. So it seems like before I missed a factor of 2 somewhere. Okay, doesn't really matter. So this was the medium. It actually was kind of hard, but it was mostly just a problem with how I made the substitution. So let's go to the hard one and pray that, oh, let's pray that this is not hard. So after yesterday, I studied a bit on how you can make ln of f of x appear. So hopefully this is something of that sort, and it can be solved quite easily. So what I'm thinking first is that I want to make ln sign appear more, because this is a weird term. So what I'm going to do is I'm going to write ln of 1 plus cosine x as, well, ln of sine squared of x over 1 minus cosine x. And I'm going to split this into 2 ln sine x minus ln 1 minus cosine x. And now I'm going to name my integral I, and it's going to be from 0 to pi of ln sine x times ln of 1 plus cosine x dx, by making this substitution that I created up here. This can be written as 2 times ln squared of sine x minus, well, dx, minus the integral from 0 to pi of ln sine x ln 1 minus cosine x dx. Now, on the interval 0 and pi, 1 plus cosine x is actually symmetric. Well, yes, it is kind of symmetric in the sense that, okay, if on this integral I go, okay, let's attempt to write this using u equals pi minus x, then du is minus dx. So this would be equal to the integral from 0 to pi ln of sine of pi minus x times ln of 1 minus cosine of pi minus x dx, or du, but they're the same thing. So sine of pi minus x is equal to sine of x, while cosine of pi minus x is minus cosine x. So this is the same as the integral from 0 to pi ln sine x times ln 1 plus cosine x dx, which is our initial integral. So we can now move this back to the other side, and we get that 2I is equal to the integral from 0 to pi, well, 2 times the integral from 0 to pi, right? Yep. ln squared of sine x dx. I'm pretty sure that, yes, sine is symmetric on the interval 0 to pi. So what we can do is we can move this back by pi over 2 by letting u equal x minus pi over 2, in which case x is pi over 2 plus u. And this becomes the integral from minus pi over 2 to pi over 2 ln squared of cosine x, cosine u, I guess. Let's be a bit consistent. Of cosine u du. Now cosine is even, so this is just 2 times the integral from 0 to pi over 2 ln squared of cosine u du. And I think we can do a t equals pi over 2 minus u. So this would just, yes, this is, okay. So finally, we need to evaluate this. And I have a good idea on how we can evaluate this. So what we're going to do is we're going to define a function. It's going to be from 0 to pi over 2. Well, it's going to be sine of t to the a dt. Now, for those of you familiar with the beta function, if you have beta of a and b, this is the same as the integral from 0 to pi over 2 sine of t to the a cosine of t to the b, well, to the 2a minus 1 to the 2b minus 1 dt. So this is actually just the beta function at a plus 1 over 2 and 1 over 2. Okay, so that's very good because the derivative of the beta function is something very interesting. So if I try to differentiate this with respect to a, of course, I should write that it's with respect to a. It's with respect to a. So what happens is the exact same function pops up, and then we also get the digamma function appearing, and it's the digamma function at the first argument plus the digamma minus the digamma function at the sum of the arguments, so a plus 2 over 2. And this is also I prime of a. Now if I differentiate again, I get, well, this is now a product, so I have to do the product of I prime of a. Oh, yes, I forgot that, well, there's also a factor of 1 over 2 here. Careful. So if I differentiate again, I get a 1 over 2 I prime of A no. If I differentiate again here, what I get is 1 over 2 times 1 over 2 times beta A plus 1 over 2 times C of A plus 1 over 2 minus C of A over 2 plus 1 squared plus 1 over 2 times 1 over 2 beta of A plus 1 over 2 1 over 2 at the trigamma functions now. Now, why am I differentiating? Well, I remind you that I of A is the integral from 0 to pi over 2 sine to the A of t dt. So if I differentiate this with respect to A using the Leibniz rule, I get, well, this is an exponential in A, so I get an ln sine of t here. If I differentiate again, I get another ln sine of t. So in the end, what I'm looking for is actually just I double prime of 0. That's my integral. So if I just go here and plug A equals 0, I should be good. Well, it is kind of annoying, but this is beta of 1 over 2, comma 1 over 2, times, well, psi of 1 over 2 minus psi of 1 squared. Plus psi prime of 1 over 2 minus psi of 1, psi prime of 1. So I'm going to find out these constants and I'll be back with you when I've found them out. Okay, so now that I've found out the values of everything, I can just plug everything in and see what happens. So, okay. So in the end, my result is pi ln squared of 2 plus pi to the third over 12. But I need to multiply that by 2. Yes, I need to multiply it by 2 here. So the result should be 2 pi ln squared 2 plus, so 2 pi ln 2 squared plus pi to the third over 6. No. Well, I'm not sure what my mistake is here. I'll take a look and let you know what could be wrong here, but everything does look correct to me, so it's probably just me forgetting a coefficient somewhere. Okay, so after looking at it, the beta function is actually twice this integral. So if I get a 2 in here, it turns out that I shouldn't be multiplying by 2 at the end of here, right? Because this is exactly my integral. This is just 2 times this, and this is also 2 times this, which is exactly the integral I want to evaluate. So the results should be the same, just without the 2 factor. Yes. Okay, so this was today's daily integral questions. They were fun. Hope you enjoyed it. Thank you for watching and see you next time.